All right, in this video, we're going to begin chapter 2 dealing with functions and graphs. And in this section 2.1, we're going to talk about the basics of functions and their graphs. And in this section, we're going to be finding the domain and range of a function. Also, we'll determine whether a relation is a function, determine whether an equation represents a function, evaluate a function, also graph functions by plotting points, use the vertical line test to identify functions, and identify intercepts from a function's graph. I think I'm going to leave this part off, identifying the intercepts from a function's graph. So let me scratch that out. Okay. All right, now, let's talk about what relations are. A relation is going to be any set of ordered pairs. So if you look down here in this example, you'll see a set of ordered pairs that is considered to be a relation. And in every relation, we can identify the domain and range. Now, the domain is a set of all first components, or we call it the first, well, just the x coordinates of the ordered pairs, because ordered pairs are of the form x comma y. So the first component would be the x coordinate. And then the range is a set of all second components, which is going to be the y coordinates in this case, when we're dealing with ordered pairs. So in this example that I just showed you, here I want to find the domain and range of this relation. So here we have a set of ordered pairs. So all we do there is just, for the domain, we just list the ordered pairs, or just list all the x coordinates. And the range, we list all of the y coordinates. So let's start with the domain. So here we list all of the x coordinates in this relation, and we list each one only once, even if they do repeat. So like the x coordinates here are the 8, as you can see. The next x coordinate is 11. The next one, -1. The next one is 0. The next one is 8, but I've already got 8 listed here, so I'm not going to list that again. And also -5. That's the domain, the set of all of your x coordinates, or the first numbers in each of the ordered pairs. The range is the set of all y coordinates, which is the second number in each of your ordered pairs. So in this case, it will be -5, and then 9, and then 6, and then +5. Now we've already got 6 listed here, so we're not going to list 6 again. And then finally, -15. Okay. So that's how we find the domain and the range of this relation. Okay. All right, here's another example of this. Let's say I want to find the domain and range of this relation. 0, 9.1, 10, 6.7, 20, 10.7, 30, 13.2, and 36, 17.4. I want to identify the domain and the range of this relation. So again, to identify the domain, we just list all of the x coordinates, or the first number in each of the ordered pairs, only once. So here, this will be 0, 10, 20, 30, and 36. So I'll write those 0, 10, 20, 30, 36. And then the range is your y coordinates here, or the second number in each of your ordered pairs. So it's going to be 9.1, 6.7, 10.7, 13.2, and 17.4. Okay. So that's how we find the domain and the range of any relation. Okay. All right, next we're going to talk about functions, because some relations are functions, or some relations can be functions, I should say. All right, now let's define what a function is. A function is a correspondence from the domain to the range such that each element of the domain corresponds to exactly one element in the range. That means in order for you to have a function, only one x can be paired with only one y value. If you have an x paired with two different y values, then that would not be a function. Or I should say two or more, an x value paired with two or more different y values, you would not have a function. Okay. Now, a function can have two different first components with the same second component. In other words, you can have two different x coordinates going to the same y coordinate, and still it would be a function. Now, a relation is not a function when two different ordered pairs have the same first component and different second components. And like I stated earlier, you can have an x coordinate paired with two or more different y values. If that's the case, then you will not have a function. All right, now let's look at some examples here. There's a couple of them. Here I want to determine from this set of ordered pairs, which is a relation, whether each one of them is a function. So in part A, I got the ordered pairs 1, 2, then 3, 4, 5, 6, and 5, 8. Would that be a function? Okay, one way of doing this would be to write or create what they call a mapping from x to y. And here we're going to list all of our x coordinates in x here, which is in this case 1, 2, and 5. And all the y coordinates will be in here 2, 4, 6, and 8. And then we're going to pair those two. So I know 1 is going to be paired with 2. Then we got 3 going to 4. Why do I have 2 here? Okay, this should be 3, not 2. Because this is 1, 3, and 5. And in this case, 3 is paired with 4. Now we got 5 paired with 6, and 5 paired with 8. This is just a visualization of the x going to the corresponding y. Notice that the 5 is paired with two different numbers, 6 and 8. So that violates the rule for being a function. So that means that this relation that you see here is not a function. Not a function. Okay, that's because you got an x value, which is 5, paired with two different y values, 6 and 8. Okay, and then part B, we got the relation 1, 2, 3, 4, 6, 5, and 8, 5. He'll want to determine whether or not that relation is a function. Okay, in this case here, I'm going to do a mapping, just like I did in part A, from x to y. and list the ordered pairs. Well, list all my x coordinates, 1, 3, 6, and 8. And then list all the y coordinates here, 2, 4, and 5. And then draw arrows from x to its corresponding y value. 1 is paired with 2. So 1 goes to 2. The 3 goes to 4. And then 6 goes to 5. And also 8 goes to 5. Now, in this case, you only got one x value going to only one y value. Now, like I stated earlier, it was possible for two different first components or two different x's going to the same y value. It's still a function. Okay, so this is a function. Okay, all right. So that's how we determine whether relations are functions. Okay, so in other words, look for a repeat in your x coordinates. If there is a repeat in your x coordinates, then that automatically tells you it's not a function. Okay, now we want to determine whether an equation is a function. Okay, a couple of definitions here. One is the independent variable. That's, of course, the variable that can be assigned any value from the domain. And usually when we're dealing with x and y, your x is always going to be your independent variable. Okay, because we can take any value from the domain and assign it for x. But the dependent variable is going to be the variable that depends upon the independent variable. Unfortunately, I can't come up with a better definition for that. It usually depends upon what x is. Okay, and usually the y will always be your dependent variable. Okay, because when you substitute x, whatever the value is for x, and you simplify, you're going to get a y value. And it usually depends upon what x is equal to. Okay. Now, there is a rule that will help you determine whether or not the equation is a function. And that's this. If the exponent for y in any equation contains an even power, like y to the second or y to the fourth, or y to the sixth, and so on, then that means that the equation will not define y as a function of x. Okay. So basically, you can look at your exponent for y. And if it's to an even power, then that equation will not be a function. Okay. Now let's look at these two examples here. In this case here, in part A, we got 2x plus y is equal to 6. I want to determine whether an equation defines y as a function of x. Okay, so I'm going to write this over here. Now, let's do this. We can solve this equation for y by moving the 2x over to the opposite side by subtracting 2x. This will mean I'm going to have y is equal to negative 2x plus 6. I'm putting the negative 2x in front. Now, this will be a function because you're only going to have one x going to only one y value. That's it. So any x value that I assign, any value that I assign to x, I'm always going to get only one y value. And by looking at the exponent for y, it is an understood 1. And that's an odd exponent, odd power. So that means this equation is a function. Now, how about part B? We got x squared plus y squared equal to 1. I want to determine whether or not that equation is a function. Now you can look at the exponent for y is y squared. That's to an even power. So automatically that's not going to be a function. Now, here's a way that you can verify that it's not a function. Okay. If I solve this equation for y, I need to subtract x squared on both sides. That would mean I'll have y squared is equal to 1 minus x squared. And I need to solve for y. So I need to, well, since it's squared, I need to take its square root on both sides. And when I do that, notice I had to include the plus or minus symbol. So that means y is equal to plus or minus the square root of 1 minus x squared. So that means for any x value, I'm going to have two different y values. One will be positive and the other one will be negative. Like for example, let's say x is equal to 0. So I'm going to take this and substitute 0 in for x. So this will be y is equal to, this will be plus or minus the square root of 1 minus 0 squared, because I'm substituting the x with 0. So this is y is equal to plus or minus. 0 squared is 0. 1 minus 0 is 1. And the square root of 1 will be 1. So my y value is going to be plus or minus 1. So at 0, I'm going to have two y values, positive 1 and negative 1. Okay. So I got an x with two y values. That means this equation is not a function. Not a function. Okay. So that's how we determine whether or not an equation is a function. Okay, now next we'll look at function notation. All right, the special notation, f with the x in parentheses, is read as f of x or f at x. And it's not f times x. It's read f of x or f at x. And that notation represents the value of the function at the number x. So you'll be given a function, what f of x is equal to. You want to find out what it's going to be at x equal whatever that number that they give you. So to evaluate a function, you just replace or substitute the independent variable with this given value. In other words, you're going to substitute x with whatever that value that's in the parentheses. And we're going to look at some where you may have to substitute the x with the algebraic expression that's given inside for f of x. Okay, like in this example here. Let's say f of x is equal to x squared minus 2x plus 7. And here we want to evaluate each of the following. Starting with, in part A, f of negative 5. Okay. So I'm starting up with a simple one, and then I'm going to progress to more difficult ones here. So that means x is negative 5. So for each x in the f of x function, we're going to substitute it with negative 5. So here, this will be equal to x is negative 5, and that's going to be squared, minus 2 times x, which is negative 5, plus 7. And then we just simplify here. Negative 5 and u squared is like negative 5 times negative 5. That's 25. And then minus 2 times negative 5 will be a plus 10. And then plus 7. And then we just add 25 and 10 and 7. You'll end up with 42. So the value of this function when x is -5 will end up being 42. Okay, next we got f of x plus 4. Now we're not looking for a numerical value, we're looking for an algebraic expression after we substitute the x with x plus 4 into this function. Okay. So here we substitute the x squared with x plus 4. Well, we substitute the x with x plus 4, but it's going to be squared, by the way, because of that square, minus 2 times substitute the x with x plus 4, and then plus 7. Okay. Now let's simplify all of this on the right side. That x plus 4 quantity squared, I'm going to write this off to the side. Because actually x plus 4 is used as a factor twice. So that means I can write this as x plus 4 times x plus 4. And then use the FOIL method for this. So here, first times the first, that's x times x squared. The outer, x times the plus 4 would be plus 4x. The inner, 4 times x will be plus 4x. And then the last times the last, 4 times 4, that'd be plus 16. Okay. Now, when I combine the two middle terms here, I'm going to end up with x squared plus 4x plus 4x is 8x, and then plus 16. That is what x plus 4 quantity squared would be. X squared plus 8x plus 16. That's for the x plus 4 quantity squared. Now I got to do minus 2 times the quantity x plus 4. That I'm going to use a distributive property. So I'm going to have to multiply the minus 2 times x. That's minus 2x. And then minus 2 times that plus 4 will be minus 8. And then bring down that plus 7. Okay, so now I need to combine like terms here. So I'm going to bring down x squared. Let's see, 8x minus 2x is a plus 6x. 16 minus 8 is 8. 8 plus 7 would be a plus 15. Okay, so the expression when x is substituted with x plus 4 in this function would be x squared plus 6x plus 15. Okay. And part C, f of negative x. Okay. Now you're going to see something like this when we get into determining whether a function is even or odd, because you're going to have to substitute the x with negative x. So here, this is what we'll do. Each x in f of x will replace it with negative x. So here's what we're going to have. F of x is equal to, this x will be replaced with negative x, and that's going to be squared, minus 2 times x is replaced with negative x, plus 7. And then simplify this. Square negative is going to be positive, so negative x times negative x will be just x squared. Minus 2 times negative x will be plus 2x, and then plus 7. And that will be as far as I can go with that problem. So here, f of negative x will end up being x squared plus 2x minus 7 after substituting the x in this function. Okay. So that's how we use function notation to substitute either a numerical value or an algebraic expression for x in the given function f of x. Okay. All right, next we'll look at graphs of functions. And here we're going to use a point by plotting points. We'll use a point plotting method here. The graph of a function is the graph of its ordered pairs. All functions with equations of the form f of x is equal to mx plus b graph as straight lines, and such functions are called linear functions. Okay. And we kind of did something like this in one of the earlier sections in chapter 1. Okay. But here it's going to be written in the form of a function. So let's say we want to graph the function f of x is equal to 2x and g of x is equal to 2x minus 3 in the same rectangular coordinate system. Select integers for x starting with -2 and ending with 2. How is the graph of g related to the graph of f? Okay, so let's start off with f of x is equal to 2x. So here, I'm just going to create a table with x and f of x. We're starting from -2, ending with 2. Okay. And f of x is 2x means for each x, we just replace, each x value will be substituted in this function in place of x. So if x is -2, I'm going to have 2 times -2, which is -4. X is -1, 2 times -1, that's -2. If x is 0, 2 times 0 is 0. If x is 1, 2 times 1 is 2. And for x is 2, 2 times 2, which is 4. All I do there is just substitute each of these and place them in place of x to get my f of x values. And these are going to be my ordered pairs here, of course. Now I write them as -2, -4, then -1, -2, 0, 0, 1, 2, and 2, 4. I'm going to plot these on the coordinate plane. All right, in this case, -2, -4 will be to the left 2 and down 4. -1, -2 will be to the left 1 and down 2. 0, 0 is at the origin. 1, 2 will be to the right 1 and up 2. And then finally 2, 4 will be to the right 2 and up 4. So those 5 points do form a straight line. And I'll connect those points. So this red line that you see here is the graph of f of x equals to 2x. Okay. And then we'll graph g of x equaling to 2x minus 3. And I'll do this on the right side. All right, so here we got x and then g of x. So I'm creating a table. And I'm still going to use -2, -1, 0, 1, and 2. Okay, so this time I'm going to take each x multiplied by 2 and subtract 3 from it. So like for x equal -2, here I'm going to have 2 times -2, which is -4, and then -4 minus 3. That's -7. And then for x equal 1, this will be 2 times -1, that's -2. -2 minus 3 is -5. And then for x is 0, 2 times 0 is 0 minus 3, which is -3. For x is 1, 2 times 1, which is 2. 2 minus 3 will be -1. And then for x is equal to 2, 2 times 2 will be 4. 4 minus 3 is 1. Okay, so these are my ordered pairs: -2, -7, -1, -5, 0, -3, 1, -1, and 2, 1. So I'm going to plot those on the coordinate plane. Let's see, I'm going to use a different color. So -2, -7 will be to the left 2 and down 7. And then -1, -5 will be to the left 1 and down 5. It's right here. 0, -3, we stay at 0 but go down to 3. 1, -1 will be to the right 1 and down 1. And 2, 1 will be to the right 2 and up 1. So you can see that those 5 points also form a straight line. So this line here that's in blue, that's going to be the graph of g of x equaling to 2x minus 3. Okay. Now, how is the graph related of g related to the graph of f? Well, the one in red is your f of x, the one in blue is your g of x. Notice that the g of x is the same as your f of x graph. The only difference here is that this graph from f to g has shifted down 3 places. It's shifted down 3 places, okay? And we call that a vertical shift, which we will talk about when we get into transformations of graphs, which is going to be section 2.5, okay? So if we want to write this out, we can say here, the graph of G has shifted down 3 places. Or you can say 3 units now. Okay. Okay, the last thing in this video we'll talk about is the vertical line test. Now, already we looked at relations and how to determine whether a relation is a function. Also, we looked at equations to determine whether or not an equation represents a function. Now we can look at a graph and determine whether or not that graph represents a function. And we're going to use what they call the vertical line test. So all you're going to do is draw a vertical line through the graph that's given to you. And the rule is this: if any vertical line intersects the graph in more than one point, the graph does not define y as a function of x. So in other words, for it to pass the vertical line test, that vertical line can only cross the graph at only one place. That's it. Like in part A of this example. Here we're going to use the vertical line test to identify graphs in which y is a function of x. Okay, so here in part A, we have the graph right here. Now, I'm going to draw a vertical line. It doesn't matter where I draw it. I could draw it on this side of on the left side of the vertical axis or on the right side of the vertical axis. Doesn't matter. Notice that this vertical line that's in red crossed this graph at only one place. Now, again, I could draw that vertical line over here. You'll see that it's still crossing the graph at only one place. So in this case here, this graph is a function based on that vertical line test. Okay, here's another example, part B. Here I want to determine whether or not that graph represents a function using the vertical line test. And notice I'm going to draw the vertical line near this hump. It's only crossing that graph at one place. Now again, I could have did it over here, draw that vertical line over here. It's only crossing the graph at one place. Or on the right side, it'll still cross the graph at one place. So this is, once again, a function. Okay. All right, now, the last example here in this video. Here I got a circle, looks like this. I want to determine whether or not it is a function. Well, notice if I draw that vertical line through that circle, this time the vertical line crosses the graph at two different places. Okay. And by the way, if you look at this y-axis right here, you can see that this circle crossed the y-axis at two different places, here and here. So this means it fails the vertical line test. That means that this graph of this circle is not a function. It is not a function. Okay. All right, so that's all I have for this video. And that does conclude this video on section 2.1, dealing with the basics of functions and their graphs. Do feel free to email me if you have any questions about any of the examples presented in this video, or if you have questions about the homework in MyMathLab.